Okay, good morning everyone. I'm the first speaker. Roman, we should start now. And thank you, the organizers, Anna and Raj. Thank you so much for doing this. Thank you, Alan, for this beautiful occasion to be here. I learned from Alan, among other things, how computational mathematics can be beautiful. And so happy birthday. My talk is joined with these three people: March, who is now in ETH Zurich, Thomas Strummer, and Asaf Ferber, my colleague at UCI. And it is really about a very simple object, quantity. How do we evaluate a norm? So the spectral norm of a random matrix, A, is obtained by just maximizing the quadratic form x transpose AY over all unit vectors x and y. The maximum is over the entire sphere, the Euclidean sphere. But sphere is kind of a complicated object, and we may ask, can we evaluate the norm on a simpler set, maybe on a discrete set? What are two most simple discrete sets in our end? One is the basis, and the other is the cube. So can we do just that? Instead of doing it on the entire Euclidean sphere, can we evaluate the spectral norm approximately on the subset? And the answer is no. You can't really evaluate the picture is switched, but you can't really evaluate it on the localized vectors like the basis 0, 0, 0, 1, 0, 0, 0, because the matrix could be all ones, and you're just picking one element. Of course, it's not going to work. And you cannot evaluate it on delocalized vectors either, the entire cube, plus minus 1, plus minus 1, plus minus, and so on, because the matrix could be localized. The matrix could be just, just 1 in one entry and 0 everywhere else, so you're wasting too much. And therefore, in fact, all localization profiles of vectors x and y have to be considered. And it's a painful situation, and many works in random matrix theory that try to evaluate the matrix norm have to deal with this fact that we have to account for all possible kind of profiles, whether we have very delocalized or localized or something in the middle. We still want to do that. So can we give up a little bit and then evaluate on such a simple set? So the good news is that you can do that. The spectral norm can be approximately evaluated on delocalized vectors, on the Boolean cube, plus minus 1, plus minus 1, plus minus 1, and so on and so forth. If you afford to give up a few rows and a few columns of a matrix A. Okay, so here is what I technically mean by that. Let's just first blindly try to evaluate the spectral norm on these vectors only. So vectors with coordinates plus 1 or minus 1. And that defines what is called the cut norm of a matrix. Just because of the normalization, it's bounded, because these vectors are not unit vectors. They have norm root n, right? So because of normalization, they are bounded not by the spectral norm, but the n times the spectral norm of A. Okay, so that's an upper bound. Is this bound sharp? Not in general, as we saw. However, if you are able to give up a few rows and columns, it is sharp. And here is a delocalization lemma. That's a kind of the main object of this talk, is that for any symmetric matrix A, and for any number of rows and columns that you are willing to give up, let's call it K, I can just find a big subset of cardinality n minus k, so I'm giving up some rows and some columns, so that the spectral norm, after we give up these columns, is bounded by the cut norm divided by k. The test case here is, think about k being a small proportion of n, like 1% of n. In this case, we'll divide by n, and if we bring it to the other side, we get that this inequality gets sharp, gets reversed, but on a submatrix. So on a submatrix and up to a constant, of constant 2, you can do that. Okay. So the funny situation is that this lemma, I've asked people and they didn't know it, and I didn't know it. However, it should have been known. It should have been known in the 80s, I think, in the 70s. kind of, it's there in the folklore of the 80s and 90s. It was never published. It was rediscovered by combinatorics people because of the importance by Alon and others, but only for graph Laplacians. But the thing is, it holds for general matrices, and I just wanted to popularize this cute little tool that I think could be useful elsewhere. So we will give a proof. We'll give two proofs, actually. One functional analytic proof, kind of the original proof that should have been discovered in the 70s and 80s, and the other one, the more modern proof. So here's the delocalization lemma again, and the functional analytic proof, I'll go very fast over it because a few people know what two-summing operators are, but this is really how you can combine existing old results in functional analysis from the 60s, 80s, 70s, and to give the proof. So the cut norm, you realize that this is actually an operator norm. It's it's an operator norm, but not from L2 into L2. It's from L infinity to L1, if you write it up. Now, every operator from L infinity to L1 is two-summing. It's a kind of a deep result that based on Grothendieck inequality, and it was discovered by Lindenstrauss and Pelczynski. You don't need to know what two-summing operator is for now, but every two-summing operator factors through L2. That's another deep result of Lindenstrauss and Pelczynski. Once you combine all the three results, you know this operator factors through L2. But factors means that there's a kind of a diagonal operator that it factors through. Now you look at this diagonal operator, there are some big entries and there are some moderate entries. You've cut out the big entries and the rest are small, and this is like identity, and so it factors through identity and you get the spectral norm. So this is kind of a little bit obscure proof because of the two summing operators, but it's there. People should have known this result from the 70s. When I thought about this, I was thinking, come on, this is a matrix result, right? It can't be that the only proof available should be using two-summing operators. It should be some matrix proof of it. Maybe some elementary proof, exhaustion or something like induction. I don't know. I don't know any elementary proof of that. It would be very, very nice to find a direct proof of this result, but I know an optimization proof. But it is a little cheating because what I did is I will basically redo this machinery in the language of optimization, but it becomes more transparent this way and simpler and a better constant too. So here is before we do the optimization proof, let's just work a little bit with the cut norm and see what it really is giving us. So this is a definition of the cut norm. When we take the maximum over the entire Boolean cube, we can shift the cube, but probably there is some constant involved. And instead of plus or minus 1, we could do 0, 1, that's fine. Yeah. But then if you look at what it really is, x, y, there are kind of indicator vectors here. So they're cutting out. So x transpose A, y is just a sum of the entries of A in this submatrix. So the cut norm just takes the maximal possible sum of entries in a submatrix. That's all it is. It becomes more useful if you think of this combinatorially. If A is an adjacency matrix of the graph, then the cut norm just counts the number of edges that crossing from one subset to the other. And let's say if adjacency matrix of a random graph, and if you look at the deviation from the expected value, then the cut norm tells us what is the worst discrepancy between the number of edges and its expected value over all possible partitions, or not even partitions, all possible subsets, I and j. So you're really like a cut. You do the cut, either matrix form or geometric form, and you want to find the max cut here. It's the maximum cut over all I and j. And that is why the cut norm is important in combinatorics, in particular graph theory, and is subject. It appears in many results, useful results, such as with Szemeredi regularity lemma by Fries and Kahn. Okay, so that's now our friend, our cut norm. And now let's try to give an optimization proof of delocalization. It is based on Grothendieck inequality. And for those that do not know Grothendieck inequality, this is a result that was proved by Alexander Grothendieck in 1956, a beautiful result with a beautiful proof, elementary looking statement that says that every matrix A satisfies this inequality. So that, let's look at it this way. Suppose the right-hand side is bounded, which means that for any x and y plus or minus 1 vectors, I can bound this quadratic form. Then the left-hand side is bounded by kind of the same quantity. And the left-hand side is, you upgrade from scalars to vectors. So instead of xi and yi being scalars, now they can be vectors in an arbitrary Hilbert space, unit vectors. Okay, so that's Grothendieck inequality. Now, the useful way to think about this is that Grothendieck inequality gives a semi-definite relaxation of the cut norm. In the right-hand side is the cut norm, right? It's a maximum over this, so it's cut norm. The left-hand side is a semi-definite program to solve. You can write it out as a semi-definite program. And so you have a semi-definite relaxation immediately. Let's express it as semi-definite program more concisely. For that, let's simplify this. Let's take these two vectors to be the same, ui's and vj's, ui being equal to vi. And so here we have the gram matrix, uiuj. Let's call it x. So this will be a gram matrix here. Gram matrix is actually it's a general thing, right? Any positive semi-definite is gram. We also know it's unit vector. Ui's are unit, and so ui should be 1. And that means that the diagonal of x is 1. So on the left-hand side, we have a gram matrix, any positive semi-definite matrix whose diagonal is 1. And the sum of aij, xij is just a trace of ax. Okay, I'm talking two elementary things here. But as you can see, the right-hand side is a cut norm. The left-hand side is a trace of ax. And because of this holds for any gram matrix, here is the semi-definite form of Grothendieck inequality. Just says that this semi-definite program, the max of it is bounded by the cut norm. Good? Okay, so that's semi-definite restatement of Grothendieck inequality. Okay, so now let's prove the localization lemma. Once you see the linear program, semi-definite program, my own instinct is to see what's a dual. This is a primal. What's a dual program? Let's do this. So this is Grothendieck's semi-definite program, the primal form. Now if you write down a little bit, the dual form, the dual SDP would be this. It's a minimum instead of maximum over the trace of a diagonal matrix that dominates A. It's an elementary exercise to show that. And so we have a dual Grothendieck inequality, which I don't know if anybody thought of this before, but it's a cool thing. So this is a dual Grothendieck inequality. Okay. So let's prove delocalization. Suppose the cut norm is bounded, let's say by 1. So if it's bounded by 1, then from here, this is bounded by 2. That means that there exists, because of the minimum, means that there exists a diagonal matrix dominating A, and whose trace is at most 2. It's diagonal, so the trace is this, it's less than 2. Okay, we know that. Well, if the trace is bounded by 2, there can only be so many big entries. If the sum is bounded by 2, it means that if I cut out the largest k entries, the rest of them will be bounded by 2 over k. That's kind of Markov's inequality. Okay, let's do that. So we just drop the largest entries. The rest of them are bounded by 2 over k. And that means that because of this diagonal matrix, it means that the matrix itself, restricted to those entries, is bounded by the identity matrix. Great. So A is bounded by Y, which is bounded by the identity matrix on that thing. Cool? So if you apply it now, if you apply the same argument, the same reasoning for minus A, you get the other inequality, and that means that we sandwiched our AI between identity and minus identity, but that means that we control the spectral norm. That's it, done. So that's a proof of delocalization lemma. With one caveat, though. The caveat is that strong duality doesn't always hold. We assume it holds, but for semi-definite program it doesn't hold, so you have to work it out a little bit. But in many situations it does, and this is one of that situations. So you just do a little exercise and convince yourself that we're okay, we're safe. Good. So that's a proof of this lemma. And there are many applications of it. One application that's kind of well established is a general strategy how to bound the spectral norm of a random matrix. It's a big question, and if you are willing to give up a constant, such as this constant 2, the Grothendieck constant, then we can do the following. Here is the strategy. First, bound the cut norm, and that could be simpler, because the max is over a simpler set, it's over a cube. And then automatically upgrade it to the spectral norm by the delocalization lemma. If you're willing to give up small number of a few rows and columns. Then if you wish, you could add them back, because there are so few of them, they may not, under some conditions, they may not affect the norm. So that's a strategy that some people employed before. And here I would like to show you an example of another theorem that should have been known before, but I didn't find anywhere. This is a cute question. You take a metric, a given matrix, not random, but you are asking what's a norm of a random submatrix of it. So you take an n by n symmetric and let's say diagonal free matrix, and you have a parameter of delta, which now you want to cut the delta n submatrix, delta n by delta n, and ask what's the norm of that thing. Okay, because we'll be using this delocalization lemma, we'll give up also a small number, a few rows and columns deterministically. So it's kind of first we do it random and then deterministic. And here is the result. So the expected value of the norm of a submatrix after we give up a few deterministic rows and columns, so maybe 1% more, is bounded by delta times the norm of the original matrix. Makes sense, right? It just scales like delta. Plus also the Frobenius norm plays a role here. So there are two terms. There is a true regime dependence. It scales down like delta, and then it scales like root delta. Now, even the existence of such a submatrix is non-trivial. Just try to prove that, forget this random thing and determine, prove that there exists a submatrix such that is bounded like this. I don't know how else can I prove it other than through this theorem. Now, annoying feature of this is that on top of the random selection, we have a little deterministic selection, right? We wish there wasn't things like that. But if we don't want to give up little sigma, the result is false, actually. It really needs to cut out things. Without sigma, there is another result. It's fine. There are results based on our work in 2008. Trop put them together, and he had a result about that. Very, very nice one. But it's not of that form. There are other terms in play there. You can also see that both of these terms are optimal. Okay, just think of, for 2 minutes, take A to be a random matrix, and it should scale like del. I think this should be the right scaling. And if you take A to be rank 1 matrix full of ones, 1, then this should be the scaling.
Can I clarify, when you say A random matrix, you mean a random symmetric matrix?
So A is a deterministic symmetric matrix, and I, the subset, is random. Yeah, so we cut out from a symmetric matrix, we cut out a symmetric submatrix, random symmetric.
And in other texts, like when you say Gaussian A, is that also?
Oh, symmetric, yeah, right.
So
Everything is symmetric, yes, correct. Yeah. Okay, now again, I'm not claiming that this result is super new. You can get it from some unpublished work, and if you apply it kind of twice, but I didn't see this result published anywhere, so I wanted to popularize this again a little bit. What was known and well known actually is like this. Frobenius norm is bounded by the spectral norm with the factor root n. So if you substitute it there, this term cancels and you get the whole right-hand side is bounded by root delta times A. That result is due to Bourgain and Safriri. So that was put there. Okay. And I'll not prove this, but this strategy is like I said, you first do the cut norm and then you upgrade it like this. Cut norm is simpler. Okay. So far so good? Okay. Okay, now how this result is applied, that will be a little bit new now. So we're coming to the newer area. And this is an application that again, I don't know, should be known in combinatorics, but combinatorics people say it's not known, so I don't know. This is just a main idea that when you take a random subgraph, it becomes a better expander automatically. Better expander than the original graph, I don't know. So what is an expander? We look at the graph on n vertices. Let's say it's a deregular graph for simplicity. And it's a spectral expander if we are able to bound its second eigenvalue of the adjacency matrix. The first eigenvalue is always, what, d or 2d? The first eigenvalue is d, I think. And the next eigenvalue, if it's very small, it's very good, becomes a very good expander. So almost like a pseudo-random graph. It effectively works as a pseudo-random graph. So the second eigenvalue is bounded by d trivially, and non-trivially, the best you can get is 2 root d minus 1. In that case, it's called the Ramanujan graph. This is the best possible expander ever. So let's measure the quality of expansion by taking the ratio between lambda and the left-hand side, like this. It's always bounded by 1. This is along Bopana bound. So the spectral expansion is always bounded by 1. It's achievable, but generally it's larger. Okay. So what happens here is we literally take the previous theorem, this one, and apply it to the adjacency matrix of the random, adjacency matrix of a n d lambda graph of an expander minus expectation. And expectation picks out the first eigenvalue. So we kill out the first eigenvalue, bound the second one. And we do this, and we work out the details, and this is what we get. Consider any n d lambda graph, any regular graph on n vertices, and whose spectral expansion is given, is alpha. Then let's consider a random subgraph plus a little bit deterministic correction, like before. So now we have a subgraph on delta n vertices. Claim it has a spectral expansion that's better in most cases. So you can't beat 1, of course, because you can never go beyond along Bopana, right? But anyway, if you are above it, you will get a progress. If delta is small, you'll get smaller than alpha. So you always will improve expansion by taking a subgraph until you hit the Ramanujan level.
Does it have any edges? I mean, you take a random subgraph. Are you taking random edges or random vertices? Oh,
you were taking the vertices. Random subgraph.
You might get no edges, right?
Almost no edges. I have to check, I think. If it's very sparse, you mean, right?
Yeah.
Yeah, if it's very sparse, I have to check. I think it's correct. You do get edges, but with this delta until you hit, yeah. Maybe if you don't get edges, then maybe this is this is false. Yeah, and if it's connected, yeah, if delta is fixed, you get some edges. Yeah, yeah, but I have to check this. But it's nothing but just working out this formula. Maybe I did something wrong with it.
I mean, sorry, you're taking a subset of like a fifth vertex, right? It's a subset of existing vertices. So aren't you guaranteed to have edges?
Yeah, but we start with something with alpha that's non-trivial. Otherwise you have a trivial. There is a big constant c involved here too, right? And so sometimes you get just the trivial results. Okay. So I'm not claiming this less smaller than 1. It's smaller than a constant times 1. So there is some room.
Okay.
So alpha has to be a little bit large to get this result working. So it means that you start with some non-trivial expander in which you have edges. Okay, and we'll have to check.
So, sorry, quick.
Yeah.
So you're doing this for adjacency matrices, but you made an interesting connection with Laplacians earlier, and the big question is, could you apply these, or people thought about applying these results for maybe
That's a good question for Laplacians, right?
Yeah.
Yeah, I don't know. That is what Alon did recently in 2010. But I don't know about that specifically. Yeah, it's a natural. Now the intuition. Why would suddenly expansion improve when you pass to random? Well, let's say random subgraph. I guess the intuition is like this. What are the obstructions to being an expander? There are very badly behaved vertices with bad degree distributions. Either they're isolated, like in the noise. Either they're isolated, or they are, on the contrary, there are too many neighbors, like stars or hubs or something like that. Those are the bad guys. But when you take a random subgraph, it tends to avoid these tiny obstructions. And plus we have a deterministic correction. We also can remove 1% of the bad guys. And maybe if you have isolated vertices, we just say remove them deterministically. We don't know what that deterministic thing does, but apparently it's able to improve that. So that's my explanation of why this phenomenon may happen. And then the last application of this expander improving corollary is the work in progress with Asaf Ferber and other people about an old conjecture that expanders are Hamiltonian. So a graph is called Hamiltonian if it has a cycle, a Hamiltonian cycle that visits every vertex exactly once, such as this blue cycle. The dense graphs always have Hamiltonian cycles. There is an old result of Dirac that says that all fold degrees are above n/2, where n is the number of vertices, then the graph is automatically Hamiltonian. What happens for sparser graphs, we do not know. What are the sufficient conditions for a graph to be Hamiltonian? In particular, a natural sufficient condition would be an expansion. If a graph is at least a little bit more than a trivial expander, then it should be Hamiltonian. That's a feeling in the area. The old conjecture of Krivilevich-Sudakov states that any ND lambda graph is Hamiltonian as soon as the spectral expansion is a little bit less than the trivial bound. Lambda is always smaller than d. Right? So a good expander is where lambda is root d, but we're not asking that. We're just asking that it is less than CD. It's out of reach for now, but very recently, Glock, Carrera, and Sudakov posted a paper that says that this Krivilevich-Sudakov conjecture is true wherever d is polynomial in n. In other words, that remember d is a degree, so you don't go you don't go down to very, very sparse graphs, but at least polynomially sparse graphs. And so we are about to finish the proof that says that this KS conjecture is true wherever d is logarithmic. Yeah, what I mean is, it's true whenever d is greater than n to the alpha, where alpha is any constant. And what we can prove using that is that KS conjecture is true wherever d is greater than log to the 8n. So the KS conjecture is true whenever the graph is at least a little bit more than a trivial expander and a little bit more than absolutely sparse. So it's above the connectivity threshold, something like that. And the key step there is to improve expansion by passing to a random subgraph when possible. And so, yeah. But I should stop here. Thank you.
So you started with the sort of norm bounds. The numerical algebra, there's a long history of norm estimators. It was think of Nick Hayem as sort of owning these things these days. Have you ever looked to see how they work in practice compared to?
Yeah, norm. You mean like approximations, not?
They're actually computed approximations, right? So you input a matrix, and you get a number which is meant to estimate the norm much more quickly than an actual.
Oh, yeah. Understood. Yeah, I do not know. That doesn't give us anything in the speed up, because computing the cut norm is actually, on the computational side, it's a bad result. Because computing cut norm is actually slower than computing the spectral norm, which you can do either by power method or spectral methods. You're right. This doesn't give anything. But the related question is what this constant 2 is at. This is Grothendieck constant actually. We do not. I don't know what's optimal constant. And whether there is a kind of a lower bound of some sort on a submatrix, or AI is greater than this, that I don't know. Good question.
Any other questions?
So, there's this notion of the graph post-equivalent
Graph, sorry?
graph post-equivalent constant. You don't know from the let's say it takes like random edges.
Oh yeah, that's a good question. So that will pick up the structure of a matrix, so to speak. Yeah. That's a good avenue to think about. The graph Grothendieck constant, that will be more adaptable to the structure of the deterministic matrix that we're looking at. We haven't. Good.
Maybe one more question? I have a quick one. The ASE is low, so the equivalent. Do you believe in that constant?
No. It should. Yeah, it could be pushed down. Absolutely. Yeah. There's no reason.
Let's take Roman.